Hello, everybody. So today what we're going to be doing is we're going to be looking through some series and seeing if they converge, diverge, and then just figuring them out in general. For problem set, it's going to be from question 5 to 9, and then question 10. I am most likely just going to show you what partial decomposition fraction, how to partially decompose fractions in one video, and then if I'm not too lazy, I'll even take it up. But most likely I'll just leave question 10 for another day. Sorry, laziness getting to me. Okay, so let's start with 5. So for 5, what we're basically given is we're given 3 different series to be more exact. And then we need to find if they converge, and if they do, find the sum, and if they don't, we gotta explain why. So let's get started. So the first sum we get is, or series we get is n equals to 1 to infinity of 1 plus 2 to the power of n over 4n minus 1. And so this part over here, I'm too lazy to write it, but keep this in mind. But in the future, I'm not going to rewrite this. In the test, you should. So let's get started. So this 4n to the power of negative 1, this negative 1 represents 1/4. So, okay, I'll rewrite it. So 1 plus 2 to the power of n over 4 to the power of n minus 1/4, or not minus, why am I writing minus? Times 1/4, because that's 4 to the power of negative 1. So then what we can do is we can get that out in front. So it would be 4 times the sum. So we're going to get sum of 1 plus 2n over 4n. So then this, we're going to separate it into two different sums to deal with each one separately. And again, the reason you can do this is because if you're thinking about it, if you have like sum of a and b, a plus b, right? And you continuously add a plus b, and you have like n term, like n equals 1 to 5. Here it's not n equals 5, but basically that we have 5 terms. And then if you think about it, you're going to get a plus b plus a plus b plus a plus b, and so on and so forth. And then what you're going to see is that if you open the brackets, you can group up the a's. So you can see that it's going to be the same thing as sum of a, n equals 1 to 5. So 5 a's plus the sum of 5 b's. So that's why we can separate them. So here, that's what I'm kind of doing. So it's going to be 4 times the sum of 1 over 4n plus the sum of 2 over 4n each. And again, we can see that these are geometric sequences then, and that they both converge because your r is less than 1. Then we get equals to 4 times sum of 1 over 4n plus sum of 2/4 to the power of n. So now we need to remember that the n over here was equal to 1. The n over here was equal to 1. So then we get, if we calculate the sum, if you remember, the sum is equal to a over 1 minus r for your geometric series. So it's going to be 4 times ra, in this case, is 1/4, because 1/4 to the power of 1 is 1/4. It's going to be 1/4 over our ratio is 1/4, so it's going to be 1 minus 1/4 plus, so here we get our a is 1/2 over 1 minus 1/2. And then we can solve this, so it's going to be 4 times 1/4 over 3/4. 1/4 over 3/4 is going to be, what is 1/4 over 3/4? It's going to be, I can't think right now clearly, 1/4 over 3/4 times 4/3. So it's going to be 1/3 plus 1, 1/3 plus 1. So then that is going to be 4/3 times 4, which is going to be 16/3. So the sum is going to converge to 16/3, and that's the sum, convergence. Perfect. So then let's look at b. So b is sum n equals to 1 to infinity. It's going to be root of 1 plus 1 over n squared. Now, this doesn't converge. And the reason this doesn't converge is because if you take the limit as n goes to infinity, the limit as n goes to infinity, what you'll see is that all of this doesn't go to 0. It actually goes to 1. And that means that this doesn't converge because you need this to at least converge to 0. So I write it out. So limit as n approaches infinity, 1 plus 1 over n squared, that is equal to root of 1 plus 1 over infinity. So that's going to approach 0. So that is equal to 1. And so since it's approaching 1 and not 0, this does not converge. Finally, for C, we are going to get sum of n equals 1 to infinity, 3 over e to the n. We can put the 3 outside, so it's going to be equal to 3 sum 1 over e to the n. So in this case, our r is smaller than 1, therefore this will converge. And we can just use our formula. So this is going to equal to 3 times our n is equal to 1 down here. So the first term is going to be 1 over e, 1 over e over 1 minus 1 over e. And then that is going to equal to, basically, so an easier way to think about it then is on the top, it's going to be 3 over e over 1 minus 1 over e. And then if you simplify it, so what are we going to get? We're going to get 3 over e over e minus 1 over e. So that these things cancel out, and it's going to be 3 over e minus 1. So this is what it converges to. Cool. Let's go into the next question. So the next question then is find the value of c. So we're looking for c if this the series which starts at n equals 2 to infinity, 1 plus c to the power of negative n equals to 2. So we know that this converges to 2. So then what we do is we know that this is a series which converges. So what we're going to do is we're going to find our a. So our a in this case is going to be 1 over 1 plus c squared, and our r is 1 over 1 plus c. And the way I got that is I just plugged in 2. Yeah. So then we know our rule for convergence, like how we calculate that. It's 1 over 1 plus c squared. So it's a over 1 minus r. So 1 over 1 plus c squared over 1 minus 1 over 1 plus c is equal to 2. So then we start calculating. So on the bottom, we get 1 over 1 plus c squared. 1 over 1 plus c squared over, this is going to be 1 plus c, so it's going to be c over 1 plus c equals to 2. So on the top then, what is it going to become? It's going to become, so it's going to be c over 1 plus c. That's how it's going to just simplify, or maybe I don't know, 1 second. Half asleep, guys, I'm sorry. 1 over 1 plus c squared times 1 plus c over c. So this cancels out. That is equal to 2. So then 2 is equal to 1 over c times 1 plus c. So then what do we get? We get that 2c. So if we multiply both sides by c times 1 plus c, so 2c squared plus 2c minus 1 is equal to 0. If we solve this quadratic equation, we get that c is equal to either -1 plus or minus root 3 over 2. Oh, sorry. Let me write it down. So c is equal to -1 plus or minus root 3 over 2. So that's our c. So now we basically need to check which of these c's work actually in our equation. So let's start. If c is equal to 1/2 times -1 minus root 3, then we kind of need to figure out what 1 plus c is equal to. Then 1 plus c is equal to, so then 1 plus c is equal to 1/2 times 1 minus root 3. And so if we plug that in, what we get is that the absolute value, because what we're trying to figure out then is 1 plus c bigger or smaller than 1? Because if it's bigger than 1, that means that our series doesn't converge, and therefore our answer can't be 2. So then if we look at it actually, so the absolute value of 1 over 1 plus c is actually going to be bigger than 1. And if you just plug it in, you'll see that. And therefore it diverges, and therefore c can't be -1 minus root 3. So then if we check c is equal to 1/2 of -1 plus root 3, what we get is that 1 plus c is equal to 1/2 times -1 plus root 3. So then if we get c and we do all our procedure, we will find that 1 over 1 plus c, so the value of it is bigger than 1, is smaller than 1 now. And you can do that just by plugging it in and see. And since it's smaller than 1, it would converge, and it would converge to 2. So everything works out. Okay, moving on to the next question. What we have is use a geometric series to express some certain continuous decimals. So the first one we get is 0.32 continuous. What we need to do is we need to express this as a geometric series. So the best way to do this is just to visualize it. So this is the same thing as 32 over 100 plus 32 over 100, 100,000, or that's 10,000, plus 32 over, we multiplied by another 100. It's going to give us, I'm going to first write it out, and then I'm going to say what it is. So yeah, so it's just going to be over 1 million. And I think we can all see the pattern then. So we get that it's 32 times series at n is equal to 0 to infinity of 1 over 100 to the power of n. And then we get our series. And if you add that up, you would see that it does in fact equal to, this is equal to 32 over 99. And if you think about it and you calculate it, you'll see that that is actually the answer that you would get. Like if you just tried to make this into a decimal, this is what you would get. Not a decimal, a fraction. Next one we have to convert is 1.717. And it's the same idea, same pattern. It's going to be 1, this time it's just going to be 1 plus 717 over 10 to the power of 3 plus 717 over 10 to the power 6 plus 717 over 10 to the power of 9, and so on and so forth. So then if we do that, what we see is that it's 1 plus 717 times the series n equals to 0 to infinity of 1 over 10 to the power of 3, all of that to the power of n. And then that would be your series. And then if you want, you could calculate what that actually is equal to. Yeah, you would find, yeah. But that's the series. Perfect. Now let's do question 8. So question 8 goes like this. You and I take turns rolling a die. The first one to roll a 6 wins. If you go first, what is the probability that you win a game? And so what you need to do here is you need to kind of write it out first to see the pattern, and then it's pretty easy to actually find the pattern. So to get probability, You need to know just a bit about probability to do this one, but basically, you roll first, and the probability that you win is 1/6. So then your opponent rolls second, and so the probability that he wins is going to be 5, or the probability that he doesn't win, because you're thinking of the probability that you win, it's going to be 5/6 squared times 1/6. So the 5/6 squared represents that you didn't roll that you didn't. So the first 5/6 here represents the probability that you didn't roll the 6, and that happens with the probability of 5/6. So then your opponent has a probability of 1/6 of winning, and then he also has the probability of 5/6 of not winning or rolling a bad roll. And so for you to roll, basically, this is your next roll. So for you to get to your next roll, there would be a 5/6 probability that you didn't roll your first one, that you didn't roll that your opponent didn't roll his second roll, and then it's a 1/6 probability of winning. Let me rephrase that from the beginning. So you roll first. There's a 1/6 probability that you win. Then on your second roll, what would need to happen is that the first roll you did is you didn't roll 1/6. You didn't roll your 6. That means with the probability of 5/6, you didn't roll that 6. Then on your second, then your opponent rolls. And with the probability of 5/6, he doesn't win. So then you have the 1/6 probability to win. And you're going to add that. And now it's going to be 5/6 to the power of 4. Because there would need to be 4 rolls that nobody got a 6 times your probability of getting that 6. And so what we see is we see our pattern basically. That it's going to be plus 5/6 to the power of 4 plus 5/6 to the power of 6 times 1/6, and so on and so forth. So hopefully then we could see our geometric series, and that geometric series is if we 1/6, we're going to factor it out, and then what we're going to be left with is sigma, and n equals at 0 because we have a 1 plus something. So to get that first term to be 1, you need the n to be equal to 0. It's 5/6 to the power of 2 to the power of n. So then your ratio is 5/6 to the power of 2, and your a is equal to 1. So then you can figure, that was horrible handwriting, but hopefully what I said made sense. So then if you actually calculate the sum of all this is going to be 1/6 times a, so it's 1/1 minus 5/6 squared, because that's the ratio. And what you would get is 6/11. So basically, if you roll first, you have a 6/11 chance of winning. So basically, the first player has a bit more chance to win than the second player, which makes sense, logically speaking. Cool. And then question 9. So for question 9, I won't do it. No, I'm kidding. The joke there was that 9 is no. Terrible joke. I'm sorry. So moving on. So it's considered the series sum n equals to 1 times n over n plus 1 factorial. And so what we basically need to do is we're going to need to find the sum of the series. But to find the sum of the series, we first need to find a pattern, then prove that pattern, and then finally we can find the sum. So the way we can find the pattern is we can see what the partial sums are. The partial sums, it's the first thing. So S at 1 is you're just adding the first term, the A1. And in this case, the first term is 1 over 2 factorial, which is going to be 1/2. Then S2 is the first term, which is 1/2, plus the second term. Now the second term is 2 over 3 factorial. So 2 over 3 factorial is 2/6, which is 1/3. So 1/3, so 1/2 plus 1/3 is equal to 5/6. So then S3 is equal to 1/2 plus 1/3 plus, now it's going to be 3. So it's 3 over 4 factorial. 3 over 4 factorial. Let's just write it down because this case it's going to be easier. And then if you add this, you're going to get 23 over 24. S4 is equal to, and then S4 is equal to half (1/3) plus 3 over 4 factorial plus 4 over 5 factorial, which is then equal to 119 over 120. So hopefully at this point you noticed the pattern, and the pattern that you might have noticed is that it's equal to, so that Sn is equal to n factorial minus 1 over n factorial. And there's another way to write that, which is equal to 1 minus 1 over n plus 1 factorial. And both of these should equal or are equal. So then we got to prove that this is in fact the truth and not just a pattern. Like, it could be a pattern, but we need to prove that this pattern is true for all of the partial sums, not just this one. So the way I'm going to do that is by induction. So what's the first? So the first one is the base case. And the base case, with the base case, what we do is we basically show that for the first term this is true, or for a term this is true, and we can show that for the S1 this is true, because for S1 we get 1/2, and 1/2 is in fact equal to n factorial minus 1, because n factorial is 2, so, which is equal to n factorial minus 1 over n factorial, because it's going to be 2 minus 1 over 2, which is 1 over 2, or 1/2. So then what we need to do is, we need to have an assumption, or we need to assume the truth, or we need to make an assumption. So our assumption is that Sn does in fact have this pattern of n factorial minus 1 over n factorial. And now we need to prove that it's true for the next term, for the nth plus 1 term. So prove for the nth plus 1 term. And so what are we basically proving? We are proving that the sum of a1 plus a2, or you can think of it as better, 1 over 2 plus, what was our second term? It was 5 over 6 plus 23 over 24 plus dot dot dot, and n factorial minus 1 over n factorial plus n plus 1 factorial minus 1 over n plus 1 factorial. So for the next term, that should be equal to n plus 1 n plus 1 sorry, I know where I made my mistake. I was just looking at it and something seemed wrong and I figured it out. So it's 23 over 24, but we're saying that the sum is equal to this, but the actual term at Sn is equal to n over n plus 1 factorial, so it's n over n plus 1 factorial plus n plus 1 over n plus 2 factorial is equal to n plus 1 factorial minus 1 over n plus 1 factorial. Cool. So now we need to prove this. So the way we can begin proving this is that we know that all of this, via our assumption, is equal to n factorial minus 1 over n factorial. So n factorial minus 1 over n factorial plus n plus 1 over n plus 2 factorial should equal to n plus 1 factorial minus 1 over n plus 1 factorial. So now what we're going to do is we're going to just look at the left side and try to make it equal to the right side. So if we do that, if we do that, then I'm just looking at my notes quickly, trying. I just don't want to make a mistake here. Over factorial n plus 1 over n plus 2 factorial, yep. So then what we can do is I'm just going to multiply, I'm going to make it the same denominator, n plus 1 factorial to add them. So we're going to get n factorial minus 1 times n plus 2 factorial plus n plus 1 times n factorial over n factorial times n plus 2 factorial. So after that, what we can do is if we open up all our brackets, we're going to get n factorial times n plus 2 factorial minus n plus 2 factorial plus n plus 1 n factorial over n factorial plus times n plus 2 factorial. So then the n factorial, what it's going to happen is this is going to cancel out with this, can cancel out with this. And then if I'm canceling out with n plus 2 factorial, so n plus 2 factorial over n factorial is just actually equal to n plus 1 times n plus 2, because n factorial is just, hopefully this makes sense. So then I'm going to get n plus 2 factorial. Let me write it out quickly. Because n plus 2 factorial is equal to n plus 2 times n plus 1 times n factorial. So over n factorial, the n factorials cancel out, and let's say we're left with n plus 1 instead of just 2. So minus n plus 1 times n plus 2 plus n plus 1 over n plus 2 n plus 2 factorial. So then what's going to happen is, just looking at my notes again, give me 1 second. I'm going to cheat a big question mark. Wait, I think I know where I made my mistake. Interestingly enough, when I was doing this in my homework, it came very easy. I'm sorry, guys. Oh, I know where I made a mistake. I didn't catch it before. I'm sorry. But actually, the mistake I made was in my assumption, and that's why nothing's adding up, is because it's not equal to n. So the partial sum, n factorial minus 1 over n factorial, it's not n factorial minus 1, because 4 factorial is not 120. It's 5 factorial. So it's actually like here. It's n plus 1 factorial minus 1 over n plus 1 factorial. There you go. And that's what the partial sum should be. So then, if I quickly restart everything, I'm sorry, guys, that you have to sit through that. My mistake. But you're going to see that everything adds up now. So if we write it correctly and have this partial sum equal to that, so n plus 1 factorial over n plus 1 factorial, then what is going on here? Then again, I'm just going to take the left side and manipulate it. So if we do the same thing, what we're going to see is that the common denominator is going to be n plus 2 factorial. So it's going to be n plus 2 factorial over, and the only thing that's happening here is that we're multiplying it by n plus 2. So n plus 1. This is a factorial. So it's going to be n plus 1 times n plus 2. So that's going to become n plus 2 factorial. It's n plus 2 factorial minus n plus 2 plus n plus 1. So if just quickly, if you didn't see that, so n plus 2 factorial, n plus 1 factorial is the only difference in these, that n plus 1 factorial times n plus 2 is going to give you n plus 2 factorial. So then I'm just getting them to the same denominator, and then I'm multiplying the top by n plus 2. So n plus 1 factorial times n plus 2 is just n plus 2 factorial. And then negative 1 times n plus 2 is just n plus 2. So then what's happening is what's happening over here. Oh, and then this should be n plus 2, n plus 2, n plus 2, because we have n plus 1. So if we add 1 to it, I totally messed everything up. But hopefully this makes sense. This should be 2 over here, because if we start with our assumption that it is n plus 1 factorial over here, that it is n plus 1 factorial minus 1 over n plus 1 factorial, then when you add another 1 for the next term, it's going to be n plus 2 factorial. So then if we go down and we see what happens, then n plus 2 factorial minus n plus n would cancel out, and then negative 2 plus 1 is minus 1. So it would become n plus 2 factorial minus 1, n plus 2 factorial. If this confused you, put it in the comments. I will redo this part. I'm sorry. Or just, yeah, put it in the comments or text me, I guess. There you go. Cool. So now we know we proved that this works, and hopefully you get it. So then what we're going to do is now we want to find the actual sum. What is the sum as n approaches infinity? And what you can see, so it's n plus 2 factorial minus 1 over n plus 2 factorial. So an easier way to view this is actually if you transform it to the other form we had, which is this is the same thing as 1 minus 1 over n plus 1 factorial. And so then if you take the limit as n approaches infinity, so limit as n approaches infinity, this is just easier because you can't really plug in infinity here because you're going to get like infinity over infinity. But if you do it this way, it's a lot easier to see. So it's going to be 1 minus. So if you plug in infinity instead of n, it's going to be 1 over infinity, which is basically going to 0. So then the answer is 1. So basically this approach is 1. And that makes sense because every time you have like 119 over 120 or 5 over 6. So you can kind of even see that it's approaching 1, that the sum is approaching 1. Cool. Hopefully that made sense. Hopefully I didn't confuse you with the many mistakes I made in question 9. But that's it. And question 10, I might upload a bit later, but I don't think it's going to be on the test anyway. But yeah, see you. If you guys really want to, just text me or tell me, and then I'll do 10 separately. Good luck tomorrow.